Yeah, first of all, thanks a lot for coming to the talk. My name is Gonçalo. I work with Parity in the Frame team, mostly focusing on the staking side of things, and that's basically what we're going to be talking about today. A quick disclaimer, I will have to gloss over a few details and do a bunch of generalizations to be able to sort of cram all this information within 20 minutes. But we're actually publishing a technical article on this topic. So if you have any questions or if you are interested about this subject, I highly recommend you to take a look at it, or just reach out to me or through the Parity forum, etc., or Polkadot forum. All right, so I would like to start from the end of this talk and put the main thesis, the main claim out there, which is that the Polkadot nomination proof of stake achieves superior economic security, capital efficiency, and fairness based on a few data analysis studies that we've done when compared to commonly used protocols out there that also have a nomination proof of stake at the expense of some added protocol complexity, which actually is completely transparent to the user. So we believe that's a good trade-off, right? I think the remaining of this talk will be an exercise on trust but verify, so I really don't want you to blindly trust this claim, and hopefully by the end you'll be able to have all the tools, background knowledge to understand what this claim means and actually reproduce all the results that we've reached to get to this conclusion by yourself. And hopefully you'll do that and reach to cool conclusions as well by yourself. Okay, but in order to do that, we'll start by a very high-level background on proof of stake and nominated proof of stake, just to make sure that we're all on the same page. And then we're going to cover in more detail and define what are these goals that we're talking about, that we're going to compare against other nominated proof of stake protocols, and then go a bit more into detail on why is it so that the Polkadot nominated proof of stake performs as it does. So we're going to have to look into some protocol details, and we'll just show then the results that we reached. Okay, so sort of the main task and the main responsibility of a proof of stake protocol is basically to select a subset of active validators that have the responsibility to produce, propose, verify blocks for the blockchain. And to select this sort of a subset of active validators from a larger set of candidates. And this is a very crucial piece of the whole proof of stake implementation and protocol, since the whole economic security, decentralization, and many other factors in the network depend on these specific building blocks. So there is, in the context of nominated proof of stake, we add one more entity that are the nominators. So the nominators are able to also contribute to the economic security of the network by locking funds and then staking and voting on the validator candidates that they believe are trustworthy and going to behave properly. And this is important also because it allows us to have more funds to back up the whole economic security of the chain, and the nominators do not have to run any of the validator infrastructure, maintenance, etc. So that's pretty cool. If we sort of think about these schematics in terms of responsibility, basically the nominators have the responsibility to select, to first lock their funds and then select the candidates, the validator candidates that they trust the most, and they're going to be better producing or operating their responsibility so that they can share the rewards. And the step from this whole sort of a diagram of nominations and candidates is going to be sort of narrowed down by this trustless election algorithm. So the election algorithm is the entity or the building block that has the responsibility to, given all the state and nominations, to basically select the active nominators for a limited time window. And this is actually an important thing that we have to consider. We really want this election algorithm to be trustless, because then again, it's a very important and crucial piece of the whole nominated proof of stake protocol, and to ensure the security, etc. And we're going to be talking a bit about that. One good way, obviously, to make sure that the algorithm runs in a trustless way is actually to run it on a blockchain. We'll see that there's other mechanisms and that can be achieve this property as well. And spoiler alert, that's what we do with the Polkadot ecosystem. So if we really focus on these trustless election algorithm. This is basically the place where we're going to be focusing our attention the most from now on. We're going to cover what are the goals that at Polkadot we try to achieve and maximize, such as economic security and many others. We're going to try to define those so where we have a good framework about what we're comparing. And then we're going to see how a few implementation details and how they influence not only the performance, but also the engineering implementation of this protocol. Then we're going to show the comparison of using the election algorithm that is used in Polkadot versus other election algorithms that are commonly used in the nominated proof of stake. Cool. So I think like one good way to start from here and sort of give a high-level view of what the Polkadot nominated proof of stake tries to achieve. We can sort of frame it in a way that its goal is to select a subset of active validators from a larger set of candidates that maximize a few properties, such as economic security, capital efficiency, fairness, and nominated freedom. So what we're going to do now is to go through each of these sort of properties and try to define them so that we understand what's happening. So economic security is probably, it's like an important word, and probably we've seen it all over the place. And it's basically, in the context of nominated proof of stake, is this sort of a metric of how much stake is backing the active validator set when the election is performed. And this metric is actually quite important because when it's coupled with a well-designed incentive structure where the slashes for misbehaving validators and as well as the rewards are proportional to the state they have backing, it sort of aligns the incentives of all the players and all the entities in the whole protocol, such as the nominators, the validators, since if they have a lot of stake, they're more likely backing. The validators are more likely to earn rewards, and so are the nominators that nominate them, but also they are more, they're going to be slashed more, and thus sort of we get into these interesting economic games. The other parameter is capital efficiency, and that's basically the ratio of stake that is locked and used to secure the network, meaning backing the active validator set after the election algorithm has run, to the total of stake locked for staking, right? So we know that, or not all the stake that is locked at a given time will actually be part of the stake that is backing the active validator set at each election, but we really want to make sure that we minimize the amount of idle locked stake that is not helping with economic security. So capital efficiency, economic security, these are like super related parameters. And obviously, we want to maximize the capital efficiency so that we also maximize economic security. So there's a few other properties under the umbrella of freedom and fairness. One of them is that we want to allow nominators to vote on multiple validators, to sort of delegate their state to multiple validators. And this is a characteristic of basically most of the nominated proof of stake protocols out there that I know, at least. But there's a few others. So we would like really to sort of avoid over and underrepresentation of the stake behind the active validator set. So let's try to think a bit about this. So we want to get to a situation where the set of validators that will produce the blocks, verify the blocks, etc., have as equally distributed stake from the nominators and from self-staking as possible, so that we don't get into this extreme situation where one of the validators, for example, has very low backing, very low stake backing, and it doesn't have as many incentives to behave properly, since the slash is not as large as it could be. So we really want to, if we know the amount of stake that is available in the active set, and we want to make sure that it's as distributed as possible to sort of align the incentives. The other one, which is also very specific to, I think, to Polkadot, is this idea of lowering the risk for the nominator stake to be non-exposed. So we want, again, going back to the capital efficiency idea, we want to make sure that if the nominator locks state, we want to try to funnel as much state to the active set as possible. And actually, the way that in practice it happens in Polkadot is that if you nominate as a nominator, let's say 10 different validators, if at least one of those 10 candidates is part of the active validator set, all of the funds that you've locked are actually going to be backing that one validator. So this is actually something pretty cool. And we'll see actually how hard and what are the consequences of having this property. And this actually also helps new validators to bootstrap. This is sort of lowers the stakes and lowers the risk for nominators to vote on validators that are basically just starting right now, that don't have a lot of street rep and don't have a lot of chances of being selected for the next active validator set right away. But since we're trying to lower also the non-exposure from nominators, it's kind of less risky to vote on new validators that you trust, and they're starting and help bootstrapping them. So this is like, now that we've kind of generally define all of these goals, I guess one of the next question is how does the election algorithm in Polkadot maximize all of these parameters, which actually some of them may even be contradictory to each other. So there's maybe some sort of a conflict with each other. So there is this very interesting property in the election algorithm used in Polkadot, which is the stake distribution that is locked. The stake distribution that is locked by the nominators is performed by the election algorithm itself. So as you can see in this image, we have the nominator A that has locked 100 tokens. This nominator A is basically voting or delegating these funds to validator candidate 1 and 2. And notice that the nominator is not explicitly telling how much of these 100 tokens are actually distributed across those validators, because that's the responsibility of the election algorithm itself. So, for example, the election algorithm, given all the other states in the staking system, may decide that all the stake that the nominator A locked is going to be backing the active, the validator 1 when is active. It can also, for one reason or another, or we'll see the reasons, but it may actually distribute in a different way. Like, for example, give 70 tokens to the validator 1 and 30 tokens to the validator 2. So this is usually something that is not used in other nominated proof-of-stake protocols, where this nominator actually explicitly tells what's the stake distribution. This has huge consequences in terms of performance, but also in terms of sort of engineering details and that we will explore in a bit. So we started actually by saying that the nominated proof-of-stake task in Polkadot is to select the subset of active validators that maximize all of these parameters. But now we can actually kind of take a step more, like a step downwards in the stack, and say that the election algorithm task, which is one of the pieces of the whole nominated proof-of-stakes protocol, has the sort of a responsibility to distribute the stake locked by the nominators across the subset of active validators, so that all of these parameters are maximized. And this is actually a NP-hard optimization problem, which requires a lot of resources, both computation, especially computation, but also storage, to calculate and to find solutions that maximize those parameters. And as we've seen, as we've said in the beginning, we really want this election algorithm to be trustless. So optimally, or we would really like to basically to run this algorithm on chain, but it's pretty much infeasible given that we're trying to run a optimization problem at scale on chain. So we will have to find out other strategies to do that. But let's put a pin on that idea. We'll go back to it in a couple of slides on how do we actually go over that. And this is actually just a quick example of, or just a diagram to show that there's not only one or two nominators or one or two validators, there may be hundreds or thousands of validators and nominators, and this is actually a pretty hard optimization problem that requires a lot of resources to make sure that the final set and stake distribution can optimize all of those parameters that we've seen so far. But that's basically the job of the election algorithm. So now I would like to kind of tell you how how does this election algorithm is actually implemented? So the Web3 Foundation research team have come up with these what we call the fragment-based election algorithm. The name is a bit funny, but for historical reasons and based on the work that this algorithm has been inspired from. The idea is that this algorithm uses a few heuristics and approximations in order to solve the election in a way that all of those parameters are maximized. Okay, but I think we put a pin on how to solve this problem, optimization problem on chain. So let's go back to it. And a very interesting result of these, the work from the Web3 Foundation folks is that although solving the computation is, solving the election algorithm is actually a optimization problem, performing the verification of a solution can be done in linear time. And this is actually pretty nice. That opened up the potential for the way actually the election algorithm works and the nominated proof of stake protocol works in Polkadot, because now we can kind of have the cake and eat it. We can have this hard optimization problem running somewhere else than on chain, and then we are able basically to get the results of those election algorithm computations and verify on chain because it's feasible. And basically verification is basically just making sure that given the input that is taken from the blockchain, running the fragment election algorithm may actually output the final solution that is being uploaded on chain. So now we get a sort of trustless election algorithm while being able to maximize all of those parameters. And that's basically what I'm lining up here. So we have these third parties that run the election algorithm of chain. They first pull the data from the chain, run these elections algorithms, submit the solution on chain, and then on chain we basically verify whether the solution makes sense given the inputs. And this actually can be done, and it's feasible, it's working, it's been working in Polkadot forever. It's pretty cool. Yeah, this is basically just sort of a summary of what we've covered. The fragment election algorithm is like the main entity that allow us to maximize or optimize the economic security, capital efficiency, fairness. User freedom is also from other parts of the protocol, and we have to it's important to understand that we can do that because of these hybrid election computation on chain and off chain. Cool. I want to really quickly go through how we actually got to the results, or at least show the summary of the results that we've got. We basically took the historical data from Polkadot, the past 1 year, I think, of election data, and then we basically computed the election solution if this stake distribution was done by the nominators, right? So basically, this sort of other model that other blockchains use, and then we compared the results and see which one was better. So there's actually in the blog post or the article that I mentioned previously, there's also a few tools that you can use to reproduce and to extract the data from Polkadot or any other chain and reproduce these results by yourself. Feel free to go and contribute and extend if you have any new ideas for these. That would be super cool. Yeah, I think I'm probably going to just gloss over this slide, but I hope by now this is already a good idea. Like you already have this sort of a notion that the biggest difference between the fragment election algorithm and sort of these commonly used election algorithms is that for the fragment election algorithm, we don't have a explicit stake distribution done by the nominators, whereas in the other election algorithms we have, which and that's basically the reason why on the fragment side, we have to run this kind of optimization problem off chain, whereas in the commonly used election algorithms out there, solving the election algorithm is basically sorting the candidates by stake, because they already have the stake assigned by definition, and then select the top N validator. So this can be easily made on chain, and there's like a few variants, plus minus, but this is more or less the idea. I have to rush up now, but I think we're almost done. So I really just want to show you high level Again, please go to the website and check the plots and all the sort of more nuanced discussion about these results. But in general, what we discovered based on our analysis is that Fragment does perform pretty well in terms of all of these kind of goals that we've covered before. So yeah, going back to the takeaways as we started. So the whole round. Hope this was useful, and I don't think we have time for questions. Okay, let me know and reach out if you have any questions or want to discuss about this. Thanks a lot for the time. Cheers.
Fantastic. I can't believe you fit so much information. So dense.